Yeah, welcome to our first Compass Wednesday seminar in this fall semester 2021. Our speaker today is Nektaria Ntaganou, and she is giving her 1 hour MPO seminar. She will defend her PhD later in this semester. And Nektaria studied physics for a bachelor's degree at the University of Athens in Greece from 2010 to 2015. And then she came to RSMAS in August 2016. She's working with Willy Kurafalou in MPO. She has one first paper as a first author under review at the moment in ocean dynamics. And she is a co-author of 4 other papers that have been published in the last years. And that's about all information she gave to me to introduce her. And now I don't even have the title of your talk, so you will show it in a moment and you can see what's the title. So yeah, take it over and give your talk.
Can you see my screen fine? Okay. Hello, everyone. Thank you, Roland, for the introduction. I would first like to acknowledge my committee members, Willy Kurafalou, Josefina Oleskoga, Igor Kamenkovic, and Matthew Lenov, as well as the agencies that supported the funding for my research. The Gulf of Mexico Research Initiative and the National Academy of Sciences, Engineering, and Medicine. I'm going to be presenting on the topographic controls and the influence of Caribbean eddies on the loop current system evolution. A little bit of an overview on the loop current system. The loop current is the main current in the Gulf of Mexico that governs the mesoscale circulation of the region. It enters through the Yucatan Strait, turns anticyclonically, and exits through the Straits of Florida, feeding into the Gulf Stream. It has variable extension phases, starting from a retracted phase, as you see in purple, up to an extended phase in the northern Gulf of Mexico. When it is extended, it forms an anticyclonic eddy, the Loop Current Eddy, that eventually detaches and propagates westward. The loop current is associated with the Gulf of Mexico Ridge eddy field, and it strongly interacts with the loop current frontal eddies that are cyclonic eddies that propagate around the loop current and facilitate the loop current eddy detachment. The Cuba anticyclones, which are formed either inside the main LC body and evolved there or released by the current and advected eastward. The West Florida anticyclones that are also released by the loop current when it impinges on the West Florida shelf and propagate northwestward along the isobats. And the Caribbean anticyclones that interact with the loop current through exchanges that take place in the Yucatan Strait. The associated eddies to the loop current are affected, among other factors, by topographic controls. For example, the formation and intensification of loop current frontal eddies, cyclones that propagate around the loop current, is affected by the topography in the Campeche Bank and the Mississippi Fan, which is a region in the northern Gulf of Mexico. Because the loop current flows through 2 straits, its evolution is affected by processes that happen in the Straits of Florida and the southwestern Florida shelf, as well as the Caribbean Sea. So there is direct topographic influence by the steep topography of the southwestern Florida shelf and inter-basin exchange with the Caribbean Sea through the Yucatan Strait. The main objective of this study is to investigate how the loop current evolution is affected by topographic controls within the Gulf of Mexico and by upstream eddy influence, meaning eddy influence that originates in the Caribbean Sea. Regarding the topographic influence, the focus is on the sole effect of the West Florida slope on the LC system. And regarding the inter-basin exchange, the approach is to investigate the influence of coherent eddy fluxes originating in the Caribbean Sea. This presentation is going to be divided in two parts. The first part is on the role of West Florida shelf topography on the loop current system variability. The results I'm about to show are from the manuscript that is now in revision in Ocean Dynamics. For the analysis of this study, of the first part, I used HICOM applied in the Gulf of Mexico at 1/25th of a degree horizontal resolution, 26 hybrid vertical layers. The vertical coordinates are isopycno in the stratified water column, terrain following at the regions close to the shelves, and isobaric in the mixed layer. This configuration of HICOM is nested in global HICOM, and it's free running, suitable for process-oriented studies. I ran three simulations, one of which, for the first one, I used realistic West Florida shelf topography, which you see on the left plot, and another two with modified West Florida shelf topography, which you see in the middle plot. The plot to your right shows the differences between the two topographies. Basically, the modified topography is up to 200 meters deeper than the realistic one, with the largest differences occurring between the 100 and 500 meter isobaths. And I modified the topography in a way that the continental shelf would be deeper and smoother. For my control experiment, the one with the realistic topography, I ran a 5-year continuous simulation from 2007 to 2011 that was based on another simulation that was initialized in 2004. So from this 5-year simulation, I used the minimum and maximum loop current northern extensions to initialize the modified topography experiments. The topominal sea experiment was initialized at the minimum loop current position, as you see in the red contour, which was at 24.5 north, and the topomaxil sea was initialized at the maximum loop current extension, as you see in the black contour, at 28.52 north. Both numerical experiments were conducted for about 2 years, and the forcing and boundary conditions are identical in all simulations. Moving on to the first results, I'm going to be showing comparisons between the control and either the topominal sea or topomaxil sea experiments. So the first and most striking difference between the control and modified experiments is the loop current extension. On the top left panel, you see the loop current extension in blue for the control and in red for the topomaxil sea. In the control experiment, the loop current quickly sets an eddy. The LC detachment is marked with a dashed blue line. It quickly sets the loop current eddy, goes back to a retracted phase. On the other hand, in the topomaxil sea, the loop current remains extended north of 26 north for almost the entire period, even after the short LC detachments and reattachments. What is connected to the loop current eddy, to the loop current extension, is the loop current axis angle, which is defined as the angle between the maximum latitude of the 17 centimeter contour and the longitude of the 17 centimeter contour inside the Yucatan channel. So basically, when the loop current is retracted, it exhibits mostly obtuse angles, and when it is extended, it exhibits acute angles. If we look at, and this is confirmed in both control and modified topography experiments, as you see in the middle panel, that shows the axis angles for the control in blue and topomaxil C in red. The axis angles for the control are larger, meaning that the loop current exhibits mostly an eastward tilt as it is retracted for almost the entire simulation, whereas in the topomaxil C, the loop current exhibits mostly a westward tilt, meaning that it is extended for almost the entire simulation. If we look at the relationship between the axis angle and the loop current extension at the lower panel, it's shown that it is mostly inversely proportional for the control experiment shown in blue, but in the topomaxil C, there is a large angle range for latitudes over 27 north, meaning that when the loop current is extended, its axis moves around covering this large range of angles, which means that its curvature is intensified. So the main point is that the topography impacts both the loop current extension and the variability of the LC axis and curvature. I would like now to introduce the theory of southwestern Florida shelf pressure point. The pressure point is located at the region of the Dry Tortugas in the southwestern Florida shelf, and it's characterized by a strong topographic gradient. It is a very important region because if you look at the topography of the West Florida shelf, all the isobats end up wrapping around the Dry Tortugas. In the modified topography, there is still a topographic gradient in the southwestern Florida shelf, not as strong this time, and the isobats are up to 25 meters deeper than the realistic case. So according to the pressure point theory, when the loop current impinges on the shelf or on the vicinity of the southwestern Florida shelf, a pressure perturbation is imposed that sets the entire West Florida shelf in motion, creating a southward flow. So also, when the loop current, according to the theory, when the loop current impinges on the shelf, it is prevented from extending northward, whereas when it moves away from the shelf, it is free to extend further into the Gulf of Mexico. This is confirmed in our control experiment after calculating the loop current proximity to the southwestern Florida shelf. The top panel shows the loop current extension in blue and the proximity of the 17 centimeter contour to the southwestern Florida shelf. The black dashed line marks the 83.5 west longitude, and basically anything east of this longitude is considered the vicinity of the pressure point, and anything west of it is considered away from the shelf. So when the loop current sets the eddy, retracts to the south, and at the same time, it is located in the vicinity of the pressure point. When it starts extending into the Gulf of Mexico, when it starts extending further into the Gulf of Mexico, it moves away from the shelf. This is not evident in the modified topography experiments, in which the loop current can be both extended and impinging on the shelf at the same time, as we see in many periods in the modified topography simulation. This implies that the interaction between the shelf slope and the current must be weakened, and that this might have an effect on the loop current extension and curvature variability. Moving on to the dynamics of the loop current evolution, I calculated potential vorticity according to Ertel's PV formula in every layer of the model, and eventually grouped in two layers, with the upper layer representing the mixed layer and the lower the rest of the ocean. The interface is at around 50 meters, at around the depth of 50 meters. The plot shows potential vorticity for the upper and lower layers for the control on the left and topominal C on the right for 2 dates early on in the simulation. Early on in the simulation, it is easier to compare, directly compare the two experiments date by date, because the loop current, the modified topography experiment is similar to the control. Later on, the modified experiment, the modified topography experiment develops into a system of its own, so a direct comparison is not possible. Looking at the upper layer, the potential vorticity in the upper layer, the differences are not that big between the control and toponomial C experiments. But if we look at the lower layers, there is intensified vorticity at the region of the southwestern Florida shelf and Straits of Florida in the control experiment, which is not evident in the modified topography experiments. Note that in these dates, since they are early on in the simulation, the loop current in both experiments is somewhat retracted and impinging on the shelf. So the differences in potential vorticity at the region of the southwestern Florida shelf and Florida Straits indicate that the weakened interaction between the current and the shelf slope in the modified topography experiment, that there is weakened interaction between the modified topography experiment and compared to the control, and implies that the presence of intensified vorticity in the southwestern Florida shelf is possibly connected to the loop current northern extension. Now, looking at transects of relative vorticity at the region of the pressure, at the area of the pressure point for the control and toponomial C at 24.5 and 25 north, there is topographic vorticity generation in the control experiment due to the interaction between the current and the shelf slope. This is not evident in our in the toponomial C experiment, in which the loop current is located at the region of the shelf, but due to the topographic modifications, the interaction is not as large. Previous studies have shown that the topographic vorticity generation is a process that can occur due to bottom stresses. So according to the pressure point theory, the loop current northern intrusion is subjected to the work done by energy dissipation in the West Florida shelf and by buoyancy due to upwelling. So if more energy is dissipated in the West Florida shelf, the work done by the loop current will not be sufficient for the current to extend into the Gulf of Mexico. This might be the mechanism in both the control and toponomial C experiments. And looking at the control, if more energy is dissipated by the topographic vorticity generation, the loop current remains retracted until it moves away from the shelf and then it is free to extend. Whereas in the toponomial C experiment, since there is not a lot of interaction, the loop current is free to extend for the entire, to extend farther into the Gulf of Mexico for the entire simulation. So this implies that changes in the topographic vorticity are connected to different loop current phases. Now, looking at the vorticity for the entire simulation, in the lower layer, in a box, integrated vorticity in a box that includes the Straits of Florida and the southwestern Florida shelf. For the control experiment, which is shown in blue in the lower panel, the potential vorticity shows some variability with the highest values occurring when it is retracted, and the lowest values occurring when it extends farther into the Gulf of Mexico. On the other hand, the potential vorticity in the lower layer of the modified topography experiment shows lower variability with generally lower values, meaning again that there is reduced interaction. I'm noting again that this does not happen because the loop current in the modified experiment is away from the shelf. It is still in the region of the shelf, but there is simply not a lot of interaction. When I talked about the pressure point theory, I said that when the loop current impinges on the shelf, there is a pressure perturbation imposed that creates a southward flow. I calculated the southward flow at 27 north for both experiments in the upper and lower layers. And if you look at the upper layer in the top panel, the differences are not that pronounced between the two experiments. However, in the lower layer, the southward flow in the control experiment is more pronounced compared to the modified topography experiment. So far, what we have is that when the loop current interacts with the topography, positive vorticity is generated that coincides with retracted LC faces, and that this process is primarily a process that has a lower layer signature. In summary, I have been looking at the interactions of the West Florida shelf topography with the loop current. The main findings are that the loop current extension is influenced by the topography of the southwestern Florida shelf. And as a result of the loop current extension, the LC axis angle is also influenced by the steep topography of the region. But what is mostly important and novel is that the loop current intrusion in the Gulf of Mexico is subject to lower layer processes that take place in the southwestern Florida shelf and Straits of Florida that are connected to the steepness and the depth of the region. And those lower layer processes are associated with the generation of cyclonic potential vorticity in the region of the pressure point in southwestern Florida shelf. Moving on to the second part. The second part is going to be on the influence of Caribbean eddies on the loop current system evolution. The results I'm about to show are part of the manuscript in preparation, and I have also contributed to a recent publication by Androulidakis et al. For the analysis of the second part, I also used HICOM, but this time a different configuration applied in the North Atlantic, including the Gulf of Mexico and the Caribbean Sea. This, the horizontal resolution is also 1/25 of a degree with 35 hybrid vertical layers, also nested in global HICOM, and it's free running as well. So since I've been looking at the effects of Caribbean eddies on the loop current evolution, I used an objective metric to detect coherent vortices. Coherent vortices are fluid elements with the same total material rotation relative to the mean rotation of the fluid mass. This method is called Lagrangian average vorticity deviation, and it can be used to detect coherent vortices that are associated with high vorticity. So vorticity itself is not objective, but if we subtract the relative vorticity averaged over the fluid and integrate over a time interval of coherence assessment, then we get an objective metric. From this metric, we can identify vortex centers as LAVT maxima and identify the coherent boundaries as the outermost convex level sets of LAVT. So in theory, coherent vortices must be convex, but in reality, in order to implement this method in the real ocean, the convexity is a little bit relaxed and some implementation is allowed. So I used LAVD to assess vortex coherence from 2010 to 2016 using the velocity fields from Atlantic HICOM. Every 15 days, south of the Yucatan Strait and throughout the entire water column. So the eddies I detected south of the Yucatan Strait, I advected for another 20 days and used only the ones that ended up in the Gulf of Mexico in this period of advection. An example of the LAVD analysis is shown in these two plots. The top plot shows the normalized LAVD field and a coherent anticyclone that was detected in the Caribbean Sea during an August 13 to 2013 LC detachment event. This and the bottom panel shows the evolution of this coherent anticyclone. The initial state is marked with the bold contour, and the rest of the contours show the evolution of this eddy in the Caribbean Sea up until it becomes a filament shown in the gray contours. Moving on to the results of the second part of the second part. So I said that I assessed coherence in the Caribbean Sea, and this plot shows the loop current extension along with the normalized area of the largest eddies that were detected south of the Yucatan Strait and eventually were advected into the Gulf of Mexico. The Yucatan Strait is defined as the black line that we see in this plot, and this is the contour is just an example of an eddy detected south of the strait and advected into the Gulf of Mexico. So this plot again shows the loop current extension along with the normalized area of the largest eddies, with the blue dots representing anticyclones and the red ones cyclones. What is interesting here is that most of the eddies that were detected south of the Yucatan Strait and crossed the channel are anticyclones, and that in some cases before the LC detachments, large anticyclones are detected. Since I've been looking at inter-basin exchange between the Caribbean Sea and the Gulf of Mexico, I calculated the integrated vorticity flux, which is shown on in the time series for the left y-axis. The integrated vorticity flux for all the eddies that were detected in all the layers of the model, which is a discrete time series because it is integrated in every 15 days, because the 15-day period was the period of coherence assessment. So in many cases in this plot, in many cases it is shown that before the loop current eddy detachment, there is increased anticyclonic vorticity flux. Sometimes it's intensified, other times it's not, but in many cases it happens. So it is an indicator that somehow the anticyclonic vorticity flux is connected to different loop current phases. Similar thing happens with the coherent anticyclonic volume. This plot shows again the discrete time series of coherent anticyclonic volume, all the anticyclones detected south of the Yucatan, along with the loop current extension. In some cases, again, before the loop current eddy detachment, the coherent anticyclonic volume is increased. So far, we have the presence of large anticyclones with high vorticity coinciding with some periods of LC shedding or detachment. But is the high vorticity or volume attributed to one eddy or multiple smaller ones, or do we see the signature in many eddies? For this reason, I started looking at individual case studies during different loop current phases, and I'm about to show two case studies, one with extended LC and one with the retracted LC. In both case studies, anticyclonic coherent eddies were detected south of the Yucatan and advected into the Gulf of Mexico. In this case, when the LC was retracted, the anticyclone that was detected south of the Yucatan is marked with the black contour. It is a large eddy, and most of the anticyclonic vorticity fluxes of this period is attributed to this eddy. It is about 200 meters deep, with the coherence signature starting at 100 meters. The signature is, the coherence signature of this eddy is evident in multiple model layers, and this is showing layer 7, just an example. So I'm going to play an animation to see the advection of this eddy into the Gulf of Mexico. And what is really interesting is that when it's advected into the Gulf of Mexico, it turns into a filament that wraps around the Loop Current Eddy. Now, the Loop Current Eddy, by the time that the anticyclone in the Caribbean was detected as coherent, the Loop Current Eddy wasn't coherent yet. It became coherent 15 days later, as you will see in the purple contour. And the rest of the purple contours in the animation show the evolution of the Loop Current Eddy. So the filament originating in the Caribbean anticyclone traces the newly detected coherent Loop Current Eddy, and nicely shows that the formation of the Loop Current Eddy is associated with anticyclonic vorticity flux through the Yucatan Strait. In order to be able to trace better the advection of the waters originating in a Caribbean anticyclone, I released particles in the black rectangle that you see on this plot, on this SSH plot, inside the Caribbean anticyclone, in all the layers in which I had the signature of this anticyclone along with the signature of the Loop Current Eddy. And I advected them for 45 days. This is an example of layer 7, around 100 meters deep. So the Caribbean waters, as you see in the animation, are mostly advected in the Loop Current Eddy that is surrounded by the non-coherent filament originating in the Caribbean anticyclone. This indicates that the Loop Current Eddy detachment is facilitated by this anticyclonic filament that comes from a Caribbean anticyclone under an extended LC. Now, looking at individual snapshots of the evolution of the Caribbean anticyclone, the Loop Current Eddy, and the particles, the Caribbean Eddy evolution is shown as a filament now in the black contour. The beginning of the Loop Current Eddy coherence is shown in the purple contour, and the rest of the plots show the evolution of both the Caribbean anticyclone and the Loop Current Eddy. So what is very interesting is that most of the particles, with a maximum of 75%, that were released in the Caribbean anticyclone end up in the Loop Current Eddy, indicating the physical connectivity between eddies in the Caribbean Sea and the Loop Current Eddy. The particles represent the water masses of the Caribbean anticyclone and show similar behavior in all the layers that the anticyclone was detected, and similar percentages, about 70%, in layers 8 and 9. Moving on to the next case study. In this case study, as you see in the SSH snapshots, the loop current was retracted and a Caribbean anticyclone was detected south of the Yucatan Strait, as you see in the red. So this anticyclone was advected into the loop current main body after as a non-coherent filament. And 15 days after that, about 15 days after, part of this non-coherent filament is traced into another coherent anticyclone, and more specifically a Cuban anticyclone inside the main LC body. This is a very good indicator of the inter-basin exchange of coherent fluxes and how it can promote eddy-to-eddy physical connectivity through filamentation. In summary, I have been looking at the interaction of Caribbean eddies and the loop current in the Gulf of Mexico. The main findings are that, first of all, coherent anticyclonic vorticity flux that originates in the Caribbean Sea is evident before loop current eddy detachments. More specifically, under extended LC phases, coherent Caribbean anticyclones can facilitate the loop current eddy detachments through the inflow of coherent anticyclonic fluxes. And during retracted LC bases, there is inter-basin exchange of coherent fluxes that can lead to eddy-to-eddy transformation through filamentation. Overall, the loop current is subject to processes that happen both in the Straits of Florida with the direct influence of the southwestern Florida shelf topography, affecting the loop current extension, and in the Yucatan Strait with anticyclonic vorticity flux attributed to coherent structures in the Caribbean Sea. For my next steps, I am planning on calculating the particle distribution during retracted LC bases to determine how the particles distribute, how particles that originate in coherent eddies in the Caribbean Sea are distributed in various anticyclonic features in the Gulf of Mexico. Other than that, I'm planning on looking into the origin of coherent Caribbean structure, of coherent Caribbean anticyclones, where exactly in the Caribbean are formed, or the water mass they are formed from, as well as deep coherent eddy signals, again in the Caribbean Sea, that could be associated with changes in the loop current bases. And with that, I can take the questions that you might have.
Okay, thank you very much. Dave Nolan?
Yeah, I have some questions. One question for each part so far. So in the first part, you presented these simulations with a modified topography, bathymetry, I should say, right? So can you just go back and talk about, what your motivation for changing the bathymetry was and how you designed that change,
Yes, so the idea behind it is to look at how the loop current evolution is affected by processes that happen in both straits. And there has been studies in the past that showed that the evolution of the loop current is affected by the topography, but they did not focus on the effects of the topography only of the southwestern Florida shelf. So I designed this experiment in a way that we only see the differences attributed to the topographic modifications. That's why I changed the topography, and I deepened it in a way that the loop current could extend into the shelf and interact or not interact with shelf the dynamics of the shelf. Because if I made it more shallow, then I would have created a wall and I wouldn't see any interactions with the shelf or any shelf dynamics in the region.
Well, I mean, was there like some period of trial and error? How did you make that big yellow stripe of it's deeper, right? So you made it softer, basically.
Yes, it's deeper. There was some period of trial and error trying to smooth out the topography so that I didn't blow up the model.
Mm-hmm.
But I had the idea in my head that I wanted to make it deeper and smoother. So I was trying different ways to do that. And when I introduced it to the model, I put the topography to the model and I saw that it was actually running. Then I didn't make any more changes.
And was this really about the pressure point theory? I mean, that you wanted to evaluate that?
So in the beginning, since I changed the entire topography of the West Florida shelf, I wanted to see differences in the entire region. But then after seeing the results, I realized that most of the differences were happening at the region of the pressure point. That's why I focused on that.
Okay. So about part two, you seem to be attributing some causality to the arrival of the anticyclonic eddy and the loop current detaching. But I noticed in those figures, I mean, there's already a loop current frontal eddy in place there.
Yes.
So, I mean, I think, well, to my knowledge, I'm not an oceanographer, right? So, but my limited knowledge, I understand that people associate the loop current frontal eddies themselves. And, sometimes they get strong and pinch off the current and sometimes they don't. There's already one there. So
yes.
Do you have any? I'm sorry, go ahead. Just you can respond.
No. Okay, so yes, of course, the loop current frontal eddies are very important for the loop current eddy detachment, but there are other factors that affect the loop current eddy detachment itself. So it's first of all the loop current frontal eddies and processes that happen in the Caribbean Sea. There have been studies in the past that actually kind of contradictory, looking at fluxes at the Yucatan Channel and how they can affect the loop current intrusion. So there are a lot of factors affecting the intrusion and the shedding of the loop current eddy, one of them being the loop current frontal eddies and instabilities that happen there, but there are also other ones happening south of the strait.
But I guess okay, I mean, do you think there's some way you could do a run like that shows some kind of causality? Like, I mean, repeat the run with like the anticyclonic eddy removed or weakened, or, you know, because I mean, I got the impression you're claiming that the loop current detachment is triggered by the arrival of the anticyclonic eddy.
It can be facilitated, but it is not the only factor that affects the loop current eddy detachment. There are other ones as well. Actually, I didn't run the second experiment. I used the outputs, but yeah, that idealized experiment could be a very good indicator to see if there's time scale differences in time scales of the loop current eddy detachment, or maybe it takes longer or shorter depending on the eddies that we have in the Caribbean Sea. And it would be much easier to figure that out with actually adding or removing eddies, because when you have a full eddy field, it's very hard to actually figure out the time span or the time scales of the detachment with all the other factors affecting it.
Okay. Anyone else?
Anyone else? No further questions, comments, positive or negative comments? Nothing? Then I just say thank you again for the nice presentation. This presentation was recorded, so you can watch it again on YouTube at a later time. And we will continue with our seminar series next Wednesday. Simge Bilgen will give her 1-hour presentation. So there is no seminar this Friday. And next Friday, I don't know, watch the emails to see if there is something or not. Thank you all for coming.
Bye, everyone.
Thank you so much.
Thank you.